In video number 95, I introduced the RedHat Shield, which turns a DCC EX system into a LocoNet command station. The basic idea is simple. If you have a working DCC EX system, all you need to do is adding a RedHat Shield on top of the stack to make it a LocoNet system that allows you to keep using your LocoNet throttles and to connect LocoNet devices like block detector modules, signal driver boards or additional boosters. Last week I received the second revision of the Shield board, so it is time to answer some of the questions you have asked and have a more detailed look at the functionality. Welcome to the IoTT channel. I am Hans Tanner. Let's start with a quick look at the latest version of the hardware. The most visible change is the additional LocoNet socket. The new board has now two LocoNet T connectors to the right that can be used to connect throttles and other devices and power them at the same time. On the long side is one LocoNet B connector that can be used to connect boosters and other devices that require the DCC information. The difference between LocoNet T and LocoNet B is the signal on pins 1 and 6 of the LocoNet cable. Type T, for throttle, carries a DC voltage and is always on as soon as the command station is powered. The Type B outlet, on the other hand, carries a low power copy of the DCC signal so that it can drive a booster. This signal is only active if track power is on or idle. If track power is off, the low power DCC signal is switched off as well, so that any connected booster will power down. The LEDs next to the LocoNet sockets indicate that the sockets are powered. Another change that comes with the new board revision is in the power supply concept. I have added a 5-volt buck converter that is connected to the 5-volt bus of the Arduino board. So the barrel connector can now be supplied with a DC voltage of 12 to 16 volts. This voltage goes to the V-in bus of the Arduino, which is connected to the motor shield and also powers the buck converter. The 5-volt supply of the Arduino is provided from the buck converter, effectively bypassing the 5-volt regulator on the Arduino board, which tends to generate a lot of heat when supplied with more than 8 volts or so. So, with this concept you can power the entire stack via the barrel connector on the RedHat Shield as long as your track current needs are not more than about 1 amp. And the voltage does not have to be higher than 16 volts. If you need more than that, you can always add a separate DC power supply to the motor shield board to increase the track current to about 2.5 amps. And if even more is needed, you can install an additional booster and control it via the LocoNet B connector. The green terminal connector is used to connect the RedHat Shield to the DCC output of the Arduino motor shield. The signal is used as input to generate the low power DCC signal on the LocoNet B socket. For the final board version, I am probably going to swap the terminal connector and the barrel jack, so that the block connector is directly above the DCC output, just to make things simpler. On the other side of the board is the pigtail for the RGB LEDs. Here you can connect a string of standard NeoPixel LEDs that can be used to display block statuses, turnout positions, etc., as I will show in a minute. And then of course there is the head connector where the IoTT stick is connected. And the short growth port cable on the left side that provides LocoNet connection to the stick. That's all for a quick review of the hardware. Of course there is more to talk about, but I will do that once the final board version is available. If you don't want to miss that, it is a good idea to subscribe to the IoTT channel and hit the bell icon. This way you will be in a premium seat when new videos become available. To turn the command station on, you simply connect the power supply and the command station is starting up. When power is disconnected, the stick shuts down automatically after 30 seconds. Before that, All runtime information is saved to the flash drive of the stick so that the next session starts exactly where you left it off. The track power status when it comes on is something you can configure in the setup screen. You can set the default value to on, off or idle, or you can set it to restore the last status it had before the shutdown. There are more configuration options as you can see. In general, I have implemented the configuration options you find in a typical LocoNet command station and then added the configuration options that are provided by the DCC export. Some of the configuration options are still work in progress though, so I will explain them in detail in a future video. One thing that is working is the power button feature I added to the side button on the lower side of the stick. Click it to toggle the track status between on and idle. On means the track is powered and the locomotives are refreshed with the DCC signal. Idle, on the other hand, means the track is powered but the only command that is sent to the locomotives is the emergency stop. That is a simple way to stop all locomotives in case of an emergency or before powering down the layout. The third function of the button is to shut down the track power, which is done by double-clicking the button. As mentioned before, this will also kill the DCC signal on the LocoNet B socket, so any attached booster will shut down track power as well. It is now very easy to configure the first NeoPixel LED, which is the one that is installed on the shield itself, to indicate the track power status. I like to show it green when power is on, blue when the track status is idle, and red if the track power is off. Selecting and operating locomotives and switches from a LocoNet throttle works like with any other LocoNet command station. You simply select the locomotive and then control it from the handheld throttle. If you have infrared or radio receivers, you connect them to LocoNet and you can use your radio or IR throttles as before. The same is true for the Wi-Fi interface or USB interfaces like the LocoBuffer. To all of these devices, the RedHat provided LocoNet looks like any other LocoNet connection, because the IoTT stick on the RedHat provides the full functionality of a typical LocoNet command station, like for example the DCS100. Next, let's have a look at how you can integrate Arduino pins as inputs for LocoNet. As you might know, you can use any unused digital pins of the Arduino to connect input devices like block detectors or buttons. Of course, on a standard Arduino Uno, that's only a few pins, but when using a Mega instead, this is a different story. And if you need more, then DCC X even offers the possibility to add I/O extender modules that let you add another 32 input lines. You can easily integrate these pins into the LocoNet address space. First, you check the Input Echo checkbox. This causes the stick to communicate changes of the pin level to LocoNet. Then you select the Inputs tab to define the pins. Note that defining the pins in this dialog automatically defines them in the Arduino configuration as well. You can add or delete pin definitions and move them up and down in the table as you like. You then define the Arduino ID number. This number should be unique, meaning you should not use the same ID number for different pins. In the pin number field, you enter the Arduino pin you want to watch using the specified ID. The logic field is currently used to determine whether the pull-up resistor on the Arduino should be activated. In the next field, you can determine what message type should be sent to LocoNet if the input status changes. Select Input Report if you want to connect a block detector. If you want to use the pin to survey the position of a turnout that has a position sensor, you can use the input to send a turnout position message by selecting Switch Report. And if you simply want to use the input to connect a button, you can select button down up and input changes will be reported as button down and button up messages to LocoNet. Click the checkbox if you want the pin definitions to be stored in the EEPROM of the Arduino. If you leave the checkbox unchecked, the settings will be reconfigured every time RedHat is starting up. Let's do an example configuration. Let's say I want to use Arduino pins 7 and 8 to connect current sensors for block detectors, and I want to display the status on LEDs 8 and 48 of the LED chain. So I activate echo messages, then define two pins for input report with a unique pin ID and the respective pin numbers and LocoNet input sensor addresses. In this example, block detectors 25 and 26. Then I click Save and Restart to save the pin definitions, and after rebooting, I select the LED chain setup tab to define the two LEDs. The first one is LED number 8, which is configured to display the status of input number 25. I want the LED to show green if the block is free and red if it is occupied. Then I copy the setup to create the definition for LED number 48, which reports the status of input number 26. After another click on Save and Restart, I can now connect a current sensor to the input, and the LED color is changing as soon as the block is occupied or released. And while preparing for this demonstration, I noticed that the behavior of the two pins is different for the same pull-up resistor setting, which I believe is a bug inside the DCC EX software. So I will have now to investigate a little more and then create a ticket in the DCC EX Discord server so that the problem can be fixed. Next, let's see how we can operate some Arduino pins from LocoNet. For the moment, I have decided to make the pins available using LocoNet Turnout addresses and commands only. To set it up, we use the Turnout tab, which works in very similar ways as the Input tab. As seen there, we first assign a unique ID to each Turnout definition. Unique means you should also avoid using numbers that you have already used for input pins. Next, you enter the LocoNet turnout address you want to use to operate this turnout. Note that there is an offset of 1 compared to the address that shows on your handheld throttle. So if you operate turnout 30 on the throttle, you will change what is defined in this setup as turnout 29. In the next field, you can select the turnout type. This is a setting that has to do with how DCC EX defines the pins. If you select the DCC option, DCC EX will ignore any pin assignments and simply send a DCC turnout command to the track. If you select C pin or V pin, RedHat will define and use a pin from a LocoNet turnout address. The difference between C pin and V pin is mainly the way how the pin is defined in DCC EX. However, the C pin setup is something that might disappear in future versions of DCC EX, as it is somewhat redundant, therefore it is not recommended to use it anymore. In any case, you can determine the logic, meaning what pin level you will get when selecting thrown or closed, and the pin number. DCC EX also provides the option to use certain pins to operate servos using some extra hardware. If you have it installed, you can select the servo option and operate the defined servo using a LocoNet switch address. For servos, you can also set minimum and maximum position as well as the rotational speed of the servo. When done, as before, click Save and Restart to save your configuration settings. If the checkbox is activated, the settings will also be stored in the Arduino. Note that even though there is a checkbox on each tab, it is only one single setting. So if you activate EEPROM storage for turnouts, it will also be used for the sensors and vice versa. Also here, let's do an example. I would like to use the two available pins 5 and 9 on the Arduino to operate two turnouts using the LocoNet turnout addresses of 30 and 35. So I define two pins with a unique ID and specify output pin number and turnout address. Remember the offset of 1, so I set the DCC addresses to 29 and 34. I click Save and Restart, and now I can operate the two pins from a handheld throttle using the selected addresses. On the oscilloscope I see the level of the output change from 0 to 5 volts and back, depending on the switch command I send. If I now want to use the outputs to operate typical snap switches or slow motion motor drives, I can use a level to pulse driver like the one I introduced in video number 78 to generate a polarized pulse of configurable length every time the position of the turnout is changing. I already showed you what can be done with the LED chain. Technically, it is identical with the LED chain that is used on the Blue Hat. So if you want to know more about what can be displayed and how to set it up, please watch video number 44. Another functionality of the IoTT stick that is available when using the RedHat Shield is the event handler, which as usual can be activated using the node configuration screen. When activated, it can be used to configure and trigger routes, including signals, and to set up ABS or APB signaling sections. I explained how to do that in the Yellow Hat Tricks playlist, starting with video number 70. Another DCC X functionality that is available from LocoNet is decoder programming, either on the main line or on the programming track. Simply use the buttons on the handheld throttle to read and write CVs and to select whether the programming commands are sent to the programming track or to the main line. In the configuration dialog, you can also specify whether the programming track should carry the main DCC signal if it is not used for programming, which I think is a very nice feature of the DCC X system that I have not seen on typical LocoNet command stations. Finally, a quick look on the available communication options. To support RedHat++, I actually have chosen to fundamentally restructure this part of the IoTT stick software in order to make it simpler and more logical. Communication really goes back to the very beginnings of the IoTT channel, as the very first video introduced a LocoNet to MQTT gateway. Over the time I added additional communication channels, mainly the LocoNet over TCP functionality, and to support the Purple Hat I recently introduced a Y-throttle client. The result of this was that the drop-down list for available communication options got longer and longer, and finding a particular option for setup became more difficult. To make things simpler, the next version of the IoTT stick software will treat command sources and available servers as two separate items. Command source options will be used to tell the system where to look for input from the command station. So the options are mainly the interface devices and the Wi-Fi based sources. Then, as before, you can select the function hat you want the stick to operate. And the new option is a list of servers that can be activated on the stick to make the information available to other devices. The options will be MQTT broker, which is the original gateway functionality, as well as a LocoNet over TCP server and a Y-throttle server. Thereby, the selection of these options is not exclusive, meaning you can activate two or even all three of them on the same stick at the same time, depending on what you want to do. For example, to connect JMRI to the RedHat, you can activate the LocoNet over TCP server and then set JMRI to connect to the server provided by RedHat. If you now open the LocoNet viewer on your JMRI screen and then change the status of one of the defined input pins, you see the incoming input report messages. And if you open the Turnout dialog window in JMRI, you are able to operate the defined turnouts using the specified LocoNet addresses from the computer. So you have full LocoNet functionality in JMRI without using a wired interface like LocoBuffer USB or similar. I am also working on the Y-throttle implementation. When done, you will be able to use software like Y-throttle or engine driver to directly connect to the Y-throttle server running on the RedHat and run locomotives from the smartphone, but without the need for an extra Wi-Fi shield on the Arduino, as the Wi-Fi connection is provided by the IoTT stick. So I hope this quick overview of the RedHat functionality has answered a good part of the questions that came up after the initial presentation. If not, please feel free to post additional requests and questions in the comments section of this video. As always, I will do my best to answer them as good as I can. And that's it for this video. I hope this information was useful or at least interesting for you. If so, please click the like button below to let me know. Doing so is a cost-free way for you to support the IoTT channel, as it causes the YouTube algorithm to suggest this video to other model railroaders. Thanks for watching and see you in the next video.